Good morning, one and all. My name is Emal Shaw, currently working as an assistant professor in Triple Department, Vigyan Nara. Now I am here to introduce the brief note about the today's guest of honor, Professor B. L. Narasimharaj Garu from NIT Warangal. Dr. B. L. Narasimharaj Garu is a professor and head of the department, currently working at the Triple Department, NIT Warangal, since from 2023 to till the date. And sir also working as a adjunct professor for SR University, Amravati. Sir has received his PhD degree from IIT Roorkee in 2012. Sir has vast experience in the field of research, academician, and also administrative roles. Sir has published various research articles, good quality journals, more than 22 research papers published at reputed journals. Sir has attended and also presented more than 62 conference papers. They got published at the various international journals. Professor B. L. Narasimharaj Garu completed 20 projects sponsored by Department of Science and Technology. So far, he has completed two research projects under his guidance. Sir also currently working on 6 research projects funded by the DST Department of Science and Technology, the few lakhs to crores. Professor B. L. Narasimharaj Garu, not only an academician, but also a researcher, he is also working as an editorial advisory board member for various reputed international journals. Sir also working as advisory member for the various international conferences organized by the various research societies. Dr. B. L. Narasimharaj Garu, professional member and fellow member at IEEE and ISTE various research societies. Dr. B. L. Narasimharaj Garu organized various SCTP programs, workshops, like this kind of funding projects, more than 22 in his credit. Thank you very much, sir, for accepting our invitation. Thank you so much. It's our pleasure. We want to learn more from you, sir. Thank you, sir.
Thank you, sir. We are happy to have a wonderful academician, Dr. B. L. Narasimharaj Garu, as our chief guest. Now, I request chief guest to address the participants on this occasion. Sir, please.
Yeah, so my dear colleagues, Professor Panindar Principal, and Dr. Rajani, Head of the Department of Electrical Engineering, and coordinators Dr. Sateesh, and other coordinators and faculty colleagues of this electrical engineering department, and participants and other student friends, friends present here. So, very good morning to all of you. And first of all, I am very delighted and pleasure to be associated with this institute even since back to maybe 1 to 10 years. So, I came to this campus earlier 3 occasions, the university campus, and also have some association with the other institute of this university at Hyderabad also. So I'm really happy for that being associated with and doing some big contribution towards this academic and research pursuits. And also, let me congratulate the coordinators for organizing this very apt and very essential course on design of advanced controller for microgrid and electric vehicles. And these are the areas, of course, they are very prominent and very essential research topics. One should continuously update and continue to work on these areas. So, therefore, see, this course gives good insights by the various experts. See, as I just go through the brochure and the schedule and this thing. Uh, I saw that the various experts derived from the various prominent institutes, premier institutes like IITs and MITs and other organizations and industry. So definitely, I'm very sure that so participants and our colleagues will receive a very good inputs on this topic of advanced control for metal and electric vehicles. Uh, yeah, so I think with this, I also hope that because we already I think it's one late, so I won't take much time. And with this, I congratulate all the participants for being a part of this event, which is sponsored by Atal, AICT Atal program. See, also the government is taking the initiation, not only this, see, this is one of the program of the government of India. So in similar way, even see, there are various schemes promoted by our government of India uh, towards mainly towards the academic and research enhancement in the country, connecting all premier institutes across the country and also across the globe as well. But so for that, really we are very proud for that kind of programs. So which support those are supported by our government of India. So one should utilize these things in effective way for all our faculty, academic and research community, so that so we can all work together to make benefit out of these learned knowledge to the societal impact. That's the main objective. See of these programs. See the devised by our government of India. So therefore, so please make a serious note on this. Don't it is just very good opportunity because we are not going to pay say much. See many programs like the free of no money, nothing need to be paid. But even with that, for that matter, even so other international programs like sport project, sport scheme, which is coordinated by IIT Kharagpur and also GAN program, Global Academic International Academic Network. So through these programs, even we are deriving the international experts and researchers to help our Indian academic and research community to make use of those experts, okay, and technological knowledge by those experts and eminent people for our benefit. Okay. So therefore, so I really congratulate these coordinators for achieving this program to our institute, this Vignan Lara Institute of Technology and Science. So with this, I wish all the participants take best out of this 1 week fruitful discussions by various experts and make use of for your research and academic pursuits. Okay, so with this, I thank the coordinators so for giving me this opportunity and inviting me here to share some of my more things. Okay, and my subject also. So thank you all once again. Thank you very much.
Thank you, sir, for your valuable words.
Thank you, distinguished guests and participants.
Now, Dr. V. Sateesh Kumar Garu will be today's schedule.
So we'll have a tea break, and after the tea break, there is a session by myself, Dr. V. Sateesh Kumar, on the fraction order control for the electrical vehicles. And after that, we'll have the lunch break at 1:30 to 2:30. And at 2:30, we'll again assemble, and we'll have a session by Dr. B. L. Narasimhan sir on the LED vehicles. So this is the lunch break for the tea.
ఇది అక్కడ దాకా పట్టినాను ఆగా ఈ చార్జ్ ఇచ్చేసి ఇక్కడ పెట్టేసేయండి ఇక్కడ పెట్టండి ఇంకా ముందు చెప్పండి ముందుకు రండి ఇటువైపు రండి ఓకే ఇక్కడ ఉన్నది పెద్దగా అవ్వట్లేదు ఇది పెద్దగా అవ్వట్లేదు
So okay, sorry for disappointing you as a first session. So I'm going to visit temple. I'll come back. I'll take 2 o'clock. 2 and continuous. Okay, compensate this 1 hour. Okay. Yeah. Thank you. అర్థమైంది అర్థమైంది నాకు అర్థమైంది మీ అర్థమైంది వాళ్ళు బాగా ఎన్ని లంచ్ జాయిన్ అవుతారు టేబుల్ కావాలి టేబుల్ ల్యాప్టాప్
Okay, sir. Not like that. Okay, sir. No, sir, not like that. Not like that. Okay, sir. Not like that.
Now I request all the participants to stay here for the event, which is led by Dr.V. Sateesh Kumar Garu, and all the second year and third year students can go to their respective classes. Thank you. I welcome Sateesh Kumar. Sateesh.
Good morning, participants. So I welcome you to the 6-day, 1 week AICT sponsored Atal FDP. So the first session of the program will be taken by me, myself, Dr. Sateesh Kumar Vavilala, currently working as Associate Professor in the Triple Department, Ignas Law Institute of Technology and Science, Vadlamudi, Guntur, Autonomous Institute. So now the today's session is a fraction order controller designed for the electrical vehicles. So first of all, before going to the details of the program, so I would like to invite, I would like to make sure that what is the difference between the fraction order controllers and integer order controllers. And first of all, why a controller is necessary for an electrical vehicle and microgrid, which is relevant to the 1 week program. So we know that many industries for the last 60 years, 50 to 60 years, many of the industry persons like paper industries, chemical industries, process control industries, cement industries, sugar industries, all these industries, they are using the proportional integral derivative controller in their implementation. And we know that a controller is required to make sure that the output follows the input, that is reference. Normally the input may be a voltage or current or speed or any other desired value or torque, okay, whatever may be the reference value, that is also called as the set point. So the output should follow this set point based upon the requirement, and this input may be sometimes will be changing frequently, or sometimes it may be always remaining constant, you know that. So for making sure that output follows the input, which is also called as the set point tracking, or simply called as the tracking problem. Okay, in the tracking problem, the output follows the input, that is the normal requirement. So to make sure that output follows the input, we will be using the proportional integral and derivative controller, also called as the PID controller. You know that it is having a simple transfer function Kp in Kp plus Ki by S plus Kd into S, where Kp, Ki, Kd are the proportional integral and derivative controllers, and these values you have to obtain by different methodologies. Normally, the operating personnel which is experienced in the industry, he will design the values of the Kp, Ka and Kd, nothing but proportional constant, integral constant and derivative constant. These control constants he will design and he will implement the controller he will tune the values of the controller and do the settings in the plant, and then the output will follow the input. This is the normal scenario which is followed from the last 50 to 60 years. Nowadays, what is happening is because of the complex situations, like the plant parameters will be changing. If you take a chemical industry, continuous stirred tank reactor will be there. It is called as the CSTR reactor. Okay, so here the continuously the plant parameters will be changing. That means for the design of the controller, the plant parameters are not remaining constant. Plant parameters are not remaining constant. So if you take this closed loop block diagram, you can see that you will be having the P and C, where P is the plant which is to be controlled by the controller C. This C is the normally PID controller is powered by the traditional industry problems. So it is a closed loop block diagram for the control system. So where C is the controller, P is the plant, and R is the reference input or set point, and Y is the output, and D is the disturbance at the output side. Now the output is fed back using some of the sensors. Okay, the output may be speed or torque or voltage or current. Okay, all these variables, position, sometimes position also, temperature, different parameters. Y can be any of the parameter. That parameter is sensed by a sensor or transducer and given to the input side, and the difference between the actual output and the desired output, that is R value, is given as the error, and that error is given to the controller. That controller is traditionally PID controller. Now the controller, what it will do? It will generate a control signal U. U is the control signal. That control signal is generated by the controller, and that control signal is given to the next actuator and then given to the plant, and then this actuator makes sure that the plant follows the input reference R. So this is the situation. Now you can see that the transfer function of the traditional PID controller is Kp plus Ki by S plus Kd into S, where Kp, Ki, Kd are the tuning parameters of the controller. This has to be designed and tuned by the operating personnel. Normally, based upon his experience, he will tune these values manually or by the trial and error method based upon the plant parameters. Now, as I told, the P, that is the plant is having a transfer function, a first order or second order or third order or higher order. Okay. Now, what is happening is this plant is not having a constant transfer function. Sometimes its parameters will be changing. That is the transfer function is not constant. It is changing with respect to time. That is one problem. Another problem is over the time progresses, you can see that you will normally how you will implement the controller. How you will implement the controller based upon the some desired set points. You will be implementing the controller with some physical parameters like RC or resistance, inductance, capacitance, or some of the op amps. All these are electronic components. Even though you are implementing digitally, for generating the control signal, you need a physical parameters, right? Resistance, inductance, capacitance, op amp, operational amplifier, all these parameters you need. Now, these physical components, as the age, that is, as the time progresses, what will happen? Its values changes. Initial value will be changed after 5 to 10 years or 20 years based upon the plant. So, what is happening? Controller which you are implementing, its values is changing. Plant, its values is changing. So this can't be handled by a simple PID controller. It is not possible. Okay. Then what you have to do is you have to go for the number of advanced controllers. So one of the advanced controllers is a fraction order controller, and this fraction order controller it can take different forms. Fraction order internal model controller, fraction order PID controller, fraction order model reference adaptive controller, fraction order model predictive controller. All these controllers are there. So now let us see one by one. What is this fraction order first? Then we will what is the difference between fraction order, integer order, and how this fraction order improves the performance of the plant. Why it is giving better performance in terms of stability, in terms of the set point tracking, in terms of the disturbance rejection. Okay, in terms of the frequency domain and time domain performance improvement. So all these parameters we will see one by one. So basically, you compare the integer order controller, this is fraction order controller. This is the normal controller you can take in any of the PID controller. Here, what are the modifications means the differentiation, yes, the power is changed. Again, the integrated power, the power is changed. So, in this case, either it can take two values only, 1 or 0. Okay, if it is 1, integrator is present. If it is 0, integrator is absent. Simple. Only two cases are there in integer order controller system. Either it is present or it is absent. Okay, if it is 0, it is absent. If it is 1, it is present. Only two values it can take. Similarly, differentiation also. The power can be either 1 or 0. 0 means it is absent. 1 means it is present. Now, the actually this fraction order controller that started from the in 1800 century by the Newton and the different scientists over the years they implemented. But after some times it got less interest, and only during the last 20 to 35 years, that is around 1990s to till date, it has gained physical implementation. The theory was there, mathematical theory, fraction order theory, it is long back, it is there. From 150 to 200 years it is available. But the physical implementation, practical knowledge, practical implementation, recently only it has gained momentum. Similar to your artificial intelligence. Now you see the compare these two controllers. What is the difference you can observe? The S power, it is no longer 0 or 1. It is another value lambda. Similarly, in the case of differentiator, the S power is not 0 or 1. It is some other value mu. Now this lambda and mu, you can choose any values between 0 to 2. You can choose any values between 0 to 2. That means non-integer values are also acceptable. In the case of fraction order controller, non-integer values, that is 0.1, 0.02, 1.1, 1.2, 2, all these values with the decimal values also you can take the powers of the S, either it is integrator or differentiator. With this small modification in the power of the integrator and differentiator, the very great results are obtained. Okay. Now since this lambda and mu are fractional values, non-integer values. Sometimes this fraction order controller is also called as the non-integer value, non-integer controller. Fraction order controller is also called as the non-integer controller. Integer means 0, 1, 2 like this. Non-integer means decimal values 0.1, 0.15, 0.18, 1.2, 1.25, 1.8, 2, 2 point, maximum 2, beyond 2 will not go. Why means if you go beyond 2, the stability problem will come. Okay, that's why the beyond 2 it is not taken. 2.1, 2.2 like that, not taken. 0 to 2 you have the freedom. 0 to 2 you can take freedom, no problem. Okay, so the fraction order is taken between 0 to 2, it is called as the fraction order controller. So you are modifying the power of integrator, power of differentiator. Now it you are calling it as the fraction order controller. Okay. So just we will see the introduction to the basics, fundamentals of the fraction order controller. So how this fraction order controller is coming and how it is different. Normally, if you write the relation between the input and output. So if you take y is the output signal, u is the input signal. Okay. So implementing any controller, you need the transfer function model of the system, right? What is transfer function? Transfer function means Laplace transform of the output by Laplace transform of the input. So if you take y of s by u of s for this system, you will be obtaining a transfer function of the system in terms of the non-integer values, that is fraction order values. So if you take in an ordinary system, this beta m minus 1 up to beta naught, they will be 3, 2, 1, 0 like that. Similarly here also 3, 2, 1, 0 if it is a third order system. Fifth order system is 5, 4, 3, 2, 1 like that. But here, these values will be between 0 to 2. These values will be between 0 to 2. Such a controller is called as the fraction order controller. So similar to the fraction order controller, the system is also having the fraction order values. That is, you can observe that the scientists they proved that some of the behaviors like thermal systems, process control industries like chemical industry, paper industry, steel industry, all these industries, the system itself it is not integer order. We are assuming that controller is fraction order, that is okay. So that means if you see the previous block diagram, this block diagram, we know till now what we have discussed. We are saying that C is a fraction order, controller is a fraction order. Now the scientists in the recent studies they found that the plant is also fraction order. P is also fraction order. Some of the systems, not all the systems, their behavior is better represented if you take the plant also having the fraction order transfer function. Okay. The examples for system is thermal system or chemical engineering, paper industries, steel industries, process control industries, especially process control industries. Process control industries means which are having the time delay, high time delay and high time constant. Okay. So they are called as the process control industries. So now you can observe that both C and P both can be fraction order. So this is the transfer function. Please observe that here the this is the differential equation. First one is the differential equation, this is the transfer function. If you take Laplace transform for this, you will obtain the transfer function. So if you take the differential equation, this derivative is a fractional derivative. Fractional derivative, not the normal derivative. So we will be having number of definitions for that. Roman RL derivative is there. Number of derivatives are there. So you can't simply implement dy by dx or d square y by dx square like that. You can't simply implement it. So you have to take the special formula for that. Right. Now, based upon the discussion till now, so you can classify the closed loop system in terms of the 4 different systems. What are the systems? So integer order controller. That is both plant and controller both are integer order. Okay. The control is also integer order, plant is also integer order. That is PID plus plant as 1 by s square plus s plus 1 like that. Now integer order system, fraction order controller. System is integer order, that is 1 by s plus 1 or 1 by s square plus s plus 1. Controller is fraction order controller, that is kp plus ki by s power 0.1 plus kd into s power 0.5 like that. Fraction order system, fraction order controller. Both the system is fraction order, plant is also, controller is also fraction order. And fraction order system, integer order controller. This is normally not preferred. Fourth one is not normally preferred. Because if the system itself is a fraction order, the integer order controller will not perform good. It will not give good results. So normally fourth one is avoided. But that combination is also possible. Now, so we have seen that the controller is designed by different methods. So we are saying kp plus ki by s plus kd by into s, or kp plus ki by s 4 lambda into kd into s 4 mu like that. You are saying that some controllers are available. How to find the values of the kp, ki, kd? How to find the values of kp, ki, kd? That is called as the tuning of the controller or design of the controller. Okay. That means you have to find the what are the values of proportional gain, integral gain, derivative gain, if it is an integer order controller. In the case of fraction order controller, what will happen? 2 more additional parameters will be coming into picture. What are the parameters? S power values in the integrator, S power value in the differentiator. So while the integer order controller has the 3 parameters kp, ki, kd, fraction order controller has the 5 parameters kp, ki, kd, lambda, mu also. So the powers of the integrator and differentiator also has to be tuned. So you may think that why you are using extra parameters unnecessarily? It is a burden, it is a complexity, but don't think like that. So even though the complexity increases, you are having a freedom. You are able to choose the parameters wisely. That means, now you all know that in your power system or power electronic applications, you may design the KPK, KD values normally, right? So what is the action of the integrator? What it will improve? Okay, what the integrator will improve? Integrator will improve the steady state error. Similarly, derivative control will improve the peak overshoot. Right? Now, my system is having my system is having only a small peak overshoot. But if you are using the derivator D, what will happen? Normally, the D is also having some other disadvantages. Okay, so if you are using the D value full value S power 1, it is not required for me. A small derivator is sufficient. One way is to control the value of the KD. If you increase the KD, it is having high derivative action. If you reduce the value of KD, derivative action is less. But in all the cases, the S power is always 1. Okay, that means it is always present. Full action is there, 100% action is there. Now, by changing the value of the power of the S along with KD, I am having one more controller on that. Okay, that means S power 0.1 is a small derivative controller. S power 1 or S power 0.9 is a full derivative controller. So I am having one more flexibility. I am having one more flexibility. That is, you can decrease or increase the control action of the derivator along with the KD. One more parameter is there. Choice is there. Okay, that is the advantage. Right. These are the different parameter tuning methods. So first one is called as the trial and error method. Trial and error method is normally used by the plant operator, and some technicians or operating personnel who are having experience from more than 10 years. They can say that, okay, for this system, this much value of KP, KD will be sufficient based on his experience, because he knows from a number of times he has designed that values, so he will guess the value manually without using any technical knowledge based on the experience. So this much of transfer function, okay, this much of values is sufficient. Some small adjustments he will do manually. There is no knowledge or theoretical knowledge supporting that adjustment based on the experience, purely based on the experience of the operating personnel. That is not scientific method, and it will also involve time consuming. Number of times he has to make the trial and error. So he will set the value Kp is equal to 2, Kp is equal to 2.5, Kp is equal to 2.25, like that he will vary and see the action based upon the output performance. If it is not good, he will change this value, but it will take some time. So it is a time consuming process, not a scientific method. Next, the second one is called as the analytical methods like direct synthesis. This we will see in detail. Next slide. Next, you all know that in your applications, neural networks, fuzzy logic, genetic algorithms. So these are the human mimicking. That means they will behave and think like a human being. Based on that, the controller will be generated. Okay. Similarly, swarm intelligence techniques. Swarm means a group of something. Swarm means a group of something. That means, like you can take particle swarm optimization, PSO algorithm. PSO algorithm, it is mimicking the birds. How the birds will search for the food, how they move in a group. Okay. Similarly, we are having a whale optimization algorithm, grey wolf optimization algorithm. Grey wolf optimization algorithm means how the wolf in the polar region, North Pole and South Pole, you will be having grey wolves. So they will follow some pattern, like they will encircle the ox, that is food, in different ways, and they will be having number of layers, that is alpha wolf, beta wolf, like that. Okay, so different animals and birds, insects, all these nature inspired algorithms, they are called as the swarm intelligence algorithms. Ant colony is there, like the number of algorithms. So how the nature is behaving, how the birds, animals, insects, how they are behaving. Based on that, we have designed some of the algorithms. They are called as the swarm algorithms. Swarm means group of something. Okay, group of birds is a particle swarm. Group of ants is called ant colony. Colony also more than one. So like this, they found the mathematical representation, and then they will implement the that algorithm. So they will run on the MATLAB or some other software. They will find the parameter values. Okay. Now we will see one by one. So what are these control techniques? Now, so coming to the today's topic, you are saying that the plant here is a electrical vehicle (EV). Okay, you are saying the plant is a EV. So you can replace this plant with any of the existing practical real life situations. So here I am following the electrical vehicle. And in the case of electrical vehicle, different parameters we are able to control like torque, speed, voltage, current, all those values or position, acceleration, any of the physical parameters you are able to control with the help of the fractional order control. Okay. And for each control you will be having different transfer functions. That is for control of the speed, one transfer function is there. Normally it is a higher order but reduce it to the first order or second order. Like that for battery management system, another transfer function. Because the input and output will be different. Mechanical system, electrical system, chemical systems, number of systems are there in the electrical vehicles. So based upon the parameter you want to control, you have to use the proper transfer function. Based on the transfer function, you will design the controller. Always a mathematical model of the plant is required. Always a mathematical model of the plant is required for the controller. If you want to design C, you should be able to give a mathematical representation for the P. So in one of my works, I have used the Gray-Wolf optimization algorithm. So here the parameters are there, number of mathematical parameters are there. So A and C are the coefficient vectors. X is the position corresponding to the best vector. X dot star. X is the present position. D is the prey position. So here in the Gray-Wolf algorithm, you will be having two stages: exploration and exploitation. Exploration and exploitation process. So using these two stages, the plant parameters will be obtained. Okay. So it will take some of the objective function. You may know that in the case of soft computing techniques, normally you need an objective function that is also called as the cost function. Objective function or cost function. So what it will do? It will reduce or minimize the value of the cost function, and then it will give the parameters Kp, Ka, Kd as the output. Okay. So you can see that when you run the algorithm, so for a number of iterations, so like 10 iterations, 20 iterations, so you will run the same algorithm number of times. Then the cost function or objective function, you can see that the red line is gradually reducing and it is reaching the minimum value. So here in this example, for 40 iterations I have run, and the objective function value is reduced from the 3500 to the almost 500. 3500 into 500 it reduced. So it will be able to give the proper controller parameter values. Right. So in the direct synthesis we have seen that earlier we have seen it is one of the methods for the control parameters tuning. So you can find number of papers based upon this direct synthesis. So here it is like I don't know anything about the controller, but I want to design based upon my requirement. That is, you will design a transfer function which is to be followed by the system. That means suppose the plant is having a second order system, second order transfer function 1 by s square plus s plus 1. So one of the poles is not giving this proper performance. Now I want the transfer function to be followed to a new value. That is overall system including the controller, closed loop controller. Okay, GC by 1 plus GC, that should be equal to a desired value. Let us say 1 by 2s square plus 2s plus 1. That is, originally the transfer function is 1 by s square plus s plus 1. I want to follow the system to be 1 by 2s square plus 2s plus 1. Okay, now we will be designing the mathematical equation. That means closed loop equation should be equal to this desired value. That is, GC is there, G into C, closed loop 1, GC by 1 plus GC is equal to 1 by 2s square plus 2s plus 1. Now when I know the value of G, so I can calculate the value of the C. Just a mathematical manipulation. Just a mathematical manipulation. So GC by 1 plus GC is equal to the desired value. Now example I am saying it is a 1 by 2s square plus 2s plus 1. So practically you can think of any other desired values based upon your requirement. So this desired transfer function, how will you decide? Okay, this desired transfer function, how will you decide? Based upon our time domain and frequency domain specifications. Based upon our time domain and frequency domain specifications. Like so the steady state error should be 0, settling time should be this much, peak hour should be 0, like that. These are the time domain specifications. Now coming to the frequency domain specifications, I will assume phase margin should be this value, gain margin should be this value. Based upon these requirements, I will first decide the transfer function. Then I will mathematically manipulate and find out the value of the C. Okay. So using the time domain and frequency domain specifications, I will find out a required or desired transfer function, equate the transfer function to the closed loop system, find out the value of the C. That is one simple method. That is called as the direct synthesis. Synthesis means deriving the controller transfer function. Synthesis means finding out and obtaining the controller transfer function. Okay. Now, normally this direct synthesis method, it is called as the analytical method. Analytical method. That is a mathematical method, hand calculation. There is no involvement of the technology. Okay. So till now we have seen two methods, direct synthesis method, and next one is called as the swarm intelligence techniques. Swarm intelligence techniques. Now we are going to the third one, that is called as the artificial intelligence methods, AI methods, also called as the AI methods. Now, for example, I am taking a power electronic control systems wherein you are having the AC-DC converter, DC-DC converter. In the case of electrical vehicles, I am saying how the AI methods can be implemented for the electrical vehicles. Okay. Now here you can see that two important methods of the AI methods are neural networks and fuzzy logic. Okay. Artificial intelligence, two important methods are neural networks and fuzzy logic. So here the artificial neural network is working as similar to our human being brain. Human being brain. So the neural models are given by the value. So it is having input layer, output layer, hidden layer. So number of layers are available. So and then you are having the weights, proper weights, okay, and then activation function, okay, all these things will be there. So these neural networks, they are used for the controller and the modeling applications, right? So if you want to model a system, okay, if you want to model a system, so a paper mathematical model is there. Sometimes what will happen is the mathematical model, it is not linear. It is not linear. Linear means superposition principle is applied. So the system model will not be 1 by s square plus s plus 1 simply. So So it will be having some of non-linearities. Different non-linearities are there. That non-linearities you can't simply express by a transfer function model. Okay, non-linear systems, they are not represented by transfer function model. Now how you implement these non-linear systems? Okay, for designing a controller, important requirement is a transfer function model is necessary, but I don't find any linear transfer function model. Then what I have to do? Replace the system, plant or system, okay, with the artificial neural network. Replace the plant with the artificial neural network, which will behave same as the system. So in that case, even though you are not having any mathematical model based upon a set of the input and output values, it will decide the model of the system. But it is not linear. Since all these activation functions on the input weights and output weights, hidden layers, all these things, they will include the non-linearity, which is not possible in the mathematical model like transfer functional model. So non-linear systems also can be represented by the neural networks. Okay, that is called as the model identification and modeling. This is one of the important control system problem. System identification and modeling. System identification and modeling. It is called as SIM. System identification and modeling. That is finding a model of the system based upon the set of input and output values. So what you will do is you will take the system, actual system, give number of inputs, find out the outputs, and this input and output pair as a matrix you will form, give that values, pair of values, input output values to the neural network, train the neural network, reduce the error and obtain a proper model of the system. Okay, that model you can use in the control purpose. That is the first important application of the artificial neural networks. That is modeling and identification. Okay. Next one is, okay, my system is having some proper model, but the controller is complex. Then neural network I can replace with the artificial neural network. Okay. Controller also I can use the neural network. So neural network is doing two purposes. One is plant, one is controller. You are able to identify the difference. So you go to the previous slide. This slide. So the neural network can do both functions. It can act as C, it can act as P. If you are using neural network for P, it is called as identification and modeling. So you are replacing P with a neural network. Similarly, replace C with also a neural network. Replace C also with a neural network. Okay. So in that case, it is called as the artificial neural network as a controller application. Both it can represent. So this is another application where your artificial intelligence is used in the case of electrical vehicles with the grid applications. So in this there are two different modes or configurations. They are called as the V2G and G2G. The vehicle to grid and grid to vehicle. And you know that most of the times the cars are parked during the office hours. That is 9 to 5. They are idle. Okay. So they are having a large battery pack, large DC voltage is available. Okay. Now you are simply not using for almost 8 to 10 hours idle situation. So what you can do during the time, you can use that battery which is placed in the electrical vehicle for supplying power to the grid. Okay, that is called as the vehicle to grid V2G model. So I am not going in depth, just I am covering the outline. Okay, so vehicle to grid. The DC voltage available in the vehicle, it is converted to the AC voltage using the inverter. Okay, so these are the vehicles. Due to the inverter, use some smoothing filter, LCL filters. Okay, then you can supply to the grid. That grid is supplying to the load. Okay, so this DC available in the vehicle converted to AC supplied to the grid. This is V2G. Okay. Similarly, if you are using the grid to charge these vehicles, it is called as the V2G, vehicle to grid. Sorry, G2V. So in the reverse operation. So reverse operation G to V, grid to vehicles. Now in this total operation, different cases I will use the artificial intelligence controllers like fuzzy logic controllers near the vehicles, neural networks, PSO, MPPT algorithms to control the supply to the vehicle and grid. Okay, so the voltage, current values, this battery management systems, all these systems, they will be using the artificial intelligence controllers like fuzzy logic. FLC is the fuzzy logic controller, ANN is the artificial neural network controllers. So in this 1 week program, different other speakers they will be discussing. Apart from the flash order controllers, we are having the other controllers also like model reference adaptive controller, model predictive controller, and then machine learning. Yes, both configurations you can use. And the parameters you can dynamically you can change controller parameters based upon the load conditions or transfer function parameter values. So one of the other controllers is called as the model reference adaptive controllers. Here the controller parameters are not constant. That is called as the adaptive controller. So where it is useful means if the plant is changing its parameters, that is if the plant is having 1 by s square plus s plus 1. So after 5 years it will become 1 by 0.1 s square plus 0.2 s plus 1. Or even though in the current situation also its chemical nature or its physical mechanical movement also changes, then it will change the parameters. The transfer function is not constant. Okay, you can't approximate the system with a constant transfer function. Continuously its parameters are changing. System transfer function is changing. Now how you will handle this one? Okay, so you can handle with the help of the adaptive controller. It is called as the adaptive controller. In the case of adaptive controller, different techniques are followed, but the model reference adaptive controller is commonly used. MRAC is called as the MRAC. So one of the algorithms we will see in the black diagram. We will see in the black diagram. So this is designed by the MIT people, that is Massachusetts Institute of Technology USA people, also called as the MIT law. It is called as the MIT law. So you are having the plant, you are having the controller, you are having the adaptation mechanism, and you are having the reference model. That means what you are doing is you are similar to the direct synthesis, similar to your direct synthesis. That means this plant has to behave similar to the reference model. అంటే మనకి కావాల్సిన టైం డొమైన్ పెర్ఫార్మెన్స్ కానీ ఫ్రీక్వెన్సీ డొమైన్ పెర్ఫార్మెన్స్ కానీ ఒక మ్యాథమెటికల్ మోడల్ రూపంలో మనం క్రియేట్ చేసుకుంటాం. సో నా సిస్టమ్ ఈ విధంగా ఉంటే బాగుంటుంది అనిపిస్తుంది. సిస్టమ్ ని మనం మార్చలేం కదా, అప్పుడు ఏం చేయాలి, మనం ఒక కంట్రోల్ ని యాడ్ చేసి సిస్టమ్ ని మనకు కావాల్సిన మోడల్ లాగా బిహేవ్ చేసేట్టుగా చేంజ్ చేసుకోవాలి. దట్ ఈస్ కాల్డ్ యాజ్ ది అడాప్టబిలిటీ. Okay, I want my plant GP of S to behave similar to the M of S. M of S is decided by me. GP of S it is not in my hands. GP of S it is not in my hands. It is as it is. Already plant is available. I can't change its parameters, but I want to behave that plant similar to what M of S will behave if R is given, YB will be obtained. Okay, like that. So I want GPS S to be behaving similar to the reference model. Okay. Now here the controller parameters also they are not constant. Continuously these values will be changing. How they will change? They will change based upon the adaptation mechanism. So you will obtain the mathematical model for the controller. You will take integration, you will take some mathematical manipulation, and continuously these parameters will be changed. In the normal KPK KD controller, once the parameters are decided, you will not change the values. KPK KD will be constant. These parameters will not change. But here, these parameters you can change continuously, automatically. మనం మాన్యువల్ ఏం చేంజ్ చేయక్కర్లేదు, ఆటోమేటికల్ గా ఇక్కడ మ్యాథమెటికల్ రిలేషన్ బట్టి ఈ వాల్యూస్ చేంజ్ అయిపోతాయి. కంటిన్యూస్లీ దే విల్ చేంజ్. సో ద కంట్రోలర్ పారామీటర్స్ ఆర్ నాట్ కాన్స్టెంట్, దే ఆర్ అడాప్టబుల్, దే ఆర్ కంటిన్యూస్లీ చేంజింగ్ based upon a mechanism, based upon some rules. So you will take errors integration, all those inputs you will take. Okay, so see what are the inputs to this mechanism? The error, okay, output, then controller input, all these are the inputs. So based upon these inputs, this theta c will be obtained. This theta c is the controller parameters. This is the controller parameters. And how these controller parameters are obtained? Based upon the values of the inputs. ఈ ఇన్పుట్స్ మీద డెసిషన్ తీసుకుని ఈ theta c ని క్యాలిక్యులేట్ చేస్తుంది. ఈ theta c ని కంట్రోలర్కి ఇస్తాం. ఓకే, ఈ ఇన్పుట్స్ ఏమేంటంటే ఎర్రర్స్, అంటే రిఫరెన్స్ వాల్యూకి అవుట్పుట్ యాక్చువల్ వాల్యూకి. చూడండి ఇక్కడ దీనికి ఇక్కడ బ్లాక్ డయాగ్రామ్ లో సమ్మేషన్ పాయింట్ ఉంది కదా, ఈ సమ్మేషన్ పాయింట్ ఇన్పుట్ ఏంటి? యాక్చువల్ మోడల్ రిఫరెన్స్ అవుట్పుట్, మన ప్లాంట్ అవుట్పుట్. మన ప్లాంట్ అవుట్పుట్ రిఫరెన్స్ అవుట్పుట్ కి తేడా ఏమైనా ఉందా? ఆల్రెడీ డిఫరెన్స్. సో ఇక్కడ E1 is equal to YP minus YM, difference between the plant output and reference model output. Reference model our desired model, దాని పారామీటర్స్ మనం డిసైడ్ చేసుకోవాలి. అంటే ఇప్పుడు టైం డొమైన్ బట్టి, ఫ్రీక్వెన్సీ డొమైన్ బట్టి మనం డిసైడ్ చేసుకోవచ్చు కదా మేడం. ఒరిజినల్ ప్లాంట్ కాదు మేడం, మన రిక్వైర్మెంట్. ఒక ప్లాంట్ ఉంది, ఆ ప్లాంట్ ఎలా బిహేవ్ చేస్తే మనకు కావాల్సిన టైం డొమైన్ స్పెసిఫికేషన్స్ వస్తాయి, దాన్ని బేస్ చేసుకుని మనము పారామీటర్స్ డిజైన్ చేసుకోవచ్చు. దీనికి రిఫరెన్స్ మోడల్ కి ప్లాంట్ కి సంబంధం లేదు. రిఫరెన్స్ మోడల్ ఈస్ డిజైన్డ్ బై ది required output, required actual output. So reference model is designed by the required output. అంటే how the plant behaves, how the plant should behave, అంటే ఎలా బిహేవ్ చేస్తే మనకు కావాల్సిన స్టెబిలిటీ వస్తుంది, మనకు కావాల్సిన టైం డొమైన్ వాల్యూస్, ఫ్రీక్వెన్సీ డొమైన్ వాల్యూస్ వస్తాయి అని బేస్ చేసుకొని మనం ఆల్రెడీ ఫిక్స్ చేసుకుని ఉంటాం ఒక మోడల్. అంటే ఒక మోడల్ ట్రాన్స్ఫర్మేషన్ తీసుకున్నాం అనుకోండి, ఒక దాని జీటా వాల్యూస్, తర్వాత ఒమేగా వాల్యూస్ ఆల్రెడీ మనం డిసైడ్ చేసుకుంటాం కదా, ఆ వాల్యూస్ బేస్ చేసుకుని ఒక ట్రాన్స్ఫర్మేషన్ ఉంటే ఇప్పుడు మనకి స్టడీ స్టేట్ ఎర్రర్ 0 వస్తుంది, పీక్ అవుట్పుట్ 0 వస్తుంది, లేదా ఫేజ్ మార్జిన్ బాగా తక్కువ ఉంటుంది, ఫేజ్ మార్జిన్ ఎక్కువ ఉంటుంది, గెయిన్ మార్జిన్ ఎక్కువ ఉంటుంది. అలా బేస్ చేసుకుని మనం దాని ప్లాట్ తీసుకుంటాం, మోడల్ ప్లాట్ తీసుకుని చెక్ చేసుకుంటాం ఈ రిఫరెన్స్ మోడల్ సూటబుల్ కాదా అని మనం చేంజ్ చేసుకోవచ్చు. ఓకే, దట్ ఈస్ నాట్ డిసైడెడ్ బై ది ప్లాంట్. ప్లాంట్ ఈ విధంగా బిహేవ్ చేస్తే బాగుంటుంది అనుకున్న మోడలే రిఫరెన్స్ మోడల్. So if there is no difference between Ym and Yp, error will be 0. Error will be 0 means then the controller will be fixed. Otherwise, the control parameters keep on changing such that Yp and Ym is equal. If Yp and Ym is equal, the control action is stopped. So now this is another method that is called as the model predictive controller, MPC. It is also called as the model predictive controller. So here number of stages are there. So optimization, state estimation, prediction. This is with respect to the that means in future what may be the plant model, what may be the plant output. You will predict, you will estimate. This is something called as the estimation model. Okay, so you will estimate that my plant should behave after some 5 seconds or after some 10 minutes. The plant output should be like this. Okay, so for this you will be using the Kalman filter. These are all mathematical manipulations in the control systems. So X tilde is there. This is the estimated model, and then state estimation will be there. That means this is a multi-input, multi-output systems, not single input. For multi-input, multi-output models, this will be useful. Okay, some of the plants will be multi-input, multi-output. MIMO systems will be there. Okay, not a single output or not single input. It will be having more than one input, more than one output. Okay, if single input model is there, transfer function is sufficient. But more than one input, more than one output is there, transfer function model is not suitable. In that case, particular case, you will be using the MIMO models, that is multi-input, multi-output models. So here you are having the plant. So you are giving the you are generating the u of k values. How the output is generated from the u of k values you will obtain, and then give to the design the Kalman filter state estimation. These are all advanced controllers. Now coming to the machine learning models. So in the case of machine learning models, so for the electrical vehicles I have taken the example. So uh, uh, what are the applications of the machine learning in the electrical vehicles I have taken? So what it will do in the case of electrical vehicles? So it can schedule the charge scheduling, that is next infrastructure planning, next charge pricing. That means how much if you go to the charging station, how much the customer should be customer should be billed. Then routing strategies, in which route if you go, the risks are minimum. Next, battery management system, that is how fast you can discharge or charge the batteries, BMS we call. This is the main important application of the artificial machine learning methods, battery management system. So you can use the machine learning methods for these applications. So these are the different areas in the electrical vehicle which are governed by the machine learning. That is energy consumption you can estimate. So you can estimate using the neural networks, and then you can state of charge SOC you can estimate for the battery. Then you can estimate the open circuit voltage, that is when there is no load connected to the battery set you can estimate. Then charging behavior. So how the charging behavior is obtained in the different cases, weather, traffic and nearby events. Okay. Then different scheduling, sales prediction. Okay. Sales prediction of the particular electrical vehicles. All next energy management, that is battery management system. So all these different areas you can use the machine learning. So if you are having any doubts, you can ask below the controllers. So we discussed about model reference adaptive controller, model predictive controller, fraction order controller, next fuzzy logic neural networks, and then these are artificial intelligence pairs. Machine learning I have not touched much. Different other controllers I have explained in detail. So if the participants are having any doubts, they can ask. Fraction order controller is better, sir. That is the recent popular one, and then neural networks and fuzzy logic. Now nowadays it is combined into single form, that is called as the adaptive neuro fuzzy inference system. So it will have all the neural networks, fuzzy logic, adaptive controller. That is called as the ANFIS. That is the latest one, and then fraction order controller. These two are the better one. Even they implemented on the physical systems also. In the NIT Nagpur, they are implementing on the electrical drives, power electronic drives. They implemented this fraction order controller. That is working fine. physical also they implement. Not only simulation, physical motor system also they implement. That is working. Non-linear case, you can implement, madam, but the performance is not good. Non-linear system, better go for the fuzzy logic or neural networks. Even fraction order control also not that much useful. Artificial intelligence, AI methods are only better in the case of non-linear systems. So if you have any other doubts, you can please ask. Fraction order control actually it is having one more application. It improves the stability margin. Normally, if you take the control system plane, you are having left hand side